Hello everyone, and welcome to this new section in which we'll look at other methods of evaluating our model other than the binary accuracy which we've been seeing so far. So in this section, we'll look at how to compare the true positives, false positives, true negatives, false negatives, the precision, the recall, the area under the curve, how to come up with confusion metrics like this, and finally how to plot out an ROC curve like this one, which permits us select the threshold more efficiently. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Let's now look at other ways of evaluating our model other than the accuracy which we've seen so far. To better understand why working with only the accuracy isn't always a great idea, we have to take into consideration the fact that our model on a test set has 94% accuracy. Now, this means that we have 6 out of 100 predictions which are actually false. Now, what if I get to the hospital and I'm told that I don't have malaria, when in fact I actually have this disease? So that said, the model predicts uninfected and I actually have the parasite in my bloodstream. Now, this particular situation becomes very dangerous because the patient gets back home thinking he or she doesn't need any treatment, whereas that patient actually has this parasite. You see that even with a 94% accuracy, we wouldn't be able to save ourselves from such chaotic model predictions. Now, in another example, you have a situation where the actual is, let's put it out here. So in another example, we can have a situation where the actual is unparasitized. So actually, you do not have this parasite, but the model predicts that you have the parasite. Now in this case, although we have a wrong prediction, we have actually a less chaotic situation as compared to this previous case here, since at least actually you are uninfected. If we consider negative, that's this negative to be uninfected, and positive to be to contain the parasite, that's P. So here we consider we have positive and then we have negative. So here we have negative uninfected and positive parasitized. Now if we let this, you will find that this first situation where actually we have the parasite and the model predicts unparasitized is known as a false negative. So here we have this false negative. And this is because the model predicts negative when it isn't actually negative. So since we have this wrong prediction for negative, we call it a false negative. And in this case where we have the model predicting parasitized, that is positive, when it's actually negative, we call this a false positive. So here we have FP and here we have FN. Now there are two other scenarios, that is with TN and TP. For the TN, we have the true negatives, and the TP, the true positives. For the TN, we have the model predicting negative when actually we are negative. That is, we have the model saying this is uninfected when actually it's uninfected. So that's a true negative. And then for the true positive, the model predicts a positive, that's parasitized, when actually it's parasitized. So that's a true positive. Now, hopefully you've understood the concepts of true negatives, true positives, false negatives, and false positives. We could then summarize all this information in this matrix known as the confusion matrix. In this confusion matrix, we have the true negatives, the number of true negatives here, the number of true positives, the number of false negatives, and the number of false positives. This means that if we have a test set of say 2,750 different data points, and then we run this or we evaluate this with our model, we'll be able to get this number of true negatives, get this number of false negatives, number of true positives, number of false positives, and hence better evaluate this model. So if we take this example where we've evaluated our model on the test set, and then this model A produces this confusion matrix, and this model B produces other confusion matrix, where here we see we have for the true negatives and true positives, we have 1,000, that's 2,000 correctly predicted data points, and then here we have 1,000, 2,000 correctly predicted data points. And then for this model A, we have 700 false positives and 50 false negatives. Whereas for model B, we have 50 false positives and 700 false negatives. Recall we had defined negative to be uninfected and positive to be parasitized. And hence, if we had to choose a model between A and B, we'll try to choose that model which minimizes the number of false negatives. So we are not saying that we shouldn't minimize the number of false positives, because we have to try to minimize all the false predictions. But then, since with the false negatives, we are telling a sick person that he or she isn't sick, this at least is worse than telling a healthy person that he or she is sick. And so we'll try to prioritize the number of false negatives, and based on this prioritization, we are going to prefer model A since we have the smaller number of false negatives. And so here we'll choose model A over model B. Now, as a quick note, you may decide to say no, negative is for parasitized and positive is for uninfected. It isn't a must that this must be tied together like this, but for clarity purposes, it's better to look at it this way, since saying you are tested negative means you're uninfected and tested positive means you're parasitized. Now, you should also note that depending on the kind of problem you want to solve, in some cases, you will want to prioritize minimizing the number of false positive over the number of false negatives. So this actually depends on the problem you're trying to solve. But in this case, we are prioritizing the number of false negatives. Now, based on what we've seen so far, we're going to introduce several new performance metrics, and all this take up these different formulas we could see right here. We have the precision, which is the number of true positives divided by the number of true positives plus the number of false positives. Recall, true positives divided by the number of true positives plus the number of false negatives. The accuracy, the number of true negatives plus the number of true positives divided by the number of true negatives plus true positives plus false negatives plus false positives. So we'll stop in this first three for now. Now, what do you notice? You'll notice that in this precision and recall, we have this true positive, and here true positive, true positive. What differentiates them is the fact that in the precision, we have false positive in the denominator, and in the recall, we have false negative in the denominator. This means that if the number of false negatives is high, that is, we have, let's say we have a constant k divided by a high value. So constant divided by a high value. So constant divided by high. Here we're going to have a low output. And so if we want to have a low recall, then we need to have a high number of false negatives. And if we want to have a low precision, then we need to have a high number of false positives. Now in our case, we're trying to minimize the number of false negatives. And since we're trying to minimize the number of false negatives, it means that we're trying to maximize the recall. Since minimizing this denominator will entail maximizing this overall TP on TP plus Fn. And so here we're trying to prioritize the recall over the precision. Now, if you look at the accuracy, you'll notice that we have Tn plus Tp and Tn plus Tp right here. Tn plus Tp, Tn plus Tp, and we have Fn plus Fp. If you are keen enough, you should see that this accuracy doesn't give any priority for whether the false negatives or the false positives. It treats these two as the same. But as we've seen previously, in the real world, in solving real world problems, many times we would have to prioritize. Hence, the accuracy may not always be the best metrics for our problem. In our case, we find that using the recall is even better than using the accuracy. As with the recall, we get to reduce, or with the recall we get to see whether our model does well at minimizing the number of false negatives. Now, we also have this F1 score, 2 times the precision times recall, this precision divided by the precision plus recall, the specificity, the number of true negatives divided by number of true negatives plus number of false positives. And then we also have this ROC plot right here. ROC stands for receiver operating characteristics. Here we have the true positive rate and the false positive rate. The true positive rate is the number of true positive divided by number of true positive plus number of false negatives, which happens to be the recall. And then the false positive rate is the number of false positives divided by number of false positives plus the number of true negatives, which if you look carefully, you'll find that is equal 1 minus the specificity, which has been defined right here. Before getting to understand this ROC plot, which we've put out here, let's recall these two models which we had described previously. That's model A and model B, where model A had a smaller number of false negatives as compared to model B. Now, if we pick out just this model A and then we are interested in reducing this, or let's say we pick out model B. Suppose we pick out model B and we're interested in reducing this number of false negatives right here. Then one solution could be that of modifying the threshold. So if we have a threshold of 0.5, meaning that above, like we have this 0.5, below 0.5 we consider negative, above 0.5 we consider positive, that is parasitized, and then below uninfected. Then what I could do here is reduce this threshold. So if I take this threshold to say a value of 0.2, let's take this here. So I've reduced this threshold now to 0.2. You'll see that for most of the predictions, our model is going to say that this is a parasitized output, since now this threshold has been reduced. This means that if we have a model prediction of 0.3, which initially would have been uninfected, now this model sees this as parasitized. And so this makes it now more difficult for our model to have false negatives, since our model now has this tendency of predicting that a given an input image is parasitized. That said, we now need to look for a way that we could automate this process. That is, we want to be able to choose this threshold correctly or rightly, because if, let's say, we take a threshold of say 0.001, it means that anytime our model predicts less than 0.01, it's uninfected, and then greater than 0.01 is parasitized. Then this will be very dangerous for the overall model performance, as now most times we would have the model predicting that the input is parasitized. And so our aim here is to pick this threshold such that this number of true positives and true negatives we've had right here don't get reduced. Now, the way we could look at this is now by using this ROC plot. With this ROC plot, what you actually have here is the different true positive rates and false positive rates you would have at a given threshold. So this means that a point picked here is just a given threshold. Now let's suppose that the threshold 0.5 is about here. So let's pick this. Let's suppose that this is 0.5. We could pick another threshold. Let's say this one is say 0.2 and so on and so forth. Let's say this one is 0.1. Now we could have another model with this different ROC plot, another one with this kind of ROC plot. But note that overall, our aim is to ensure that this false positive rates is minimized and the true positive rate is maximized. So if we have an ROC plot which is like this, so let's redraw this. If we have this kind of ROC plot, that is one that goes up straight like this and then comes this way, we have this right here. So if we have this kind of ROC plot, then we will be able to pick out this threshold right here, 0. Say x. We'll be able to pick this threshold because at this threshold, for this threshold at this point, the true positive rate is at its highest value, that is of 1, and then the false positive rate is at its lowest possible value, that is of 0. So here we have 1 and then 0. So here we go, we have this, and then we pick out this threshold. Now this value of x could be 5, could be 4, or whatever. So we have 0. Whatever value will lead us to this. Nonetheless, many times we wouldn't have this kind of plots, so we will do it plots which will look like this, this, and so on and so forth. Now, once given a plot like this one, let's suppose we have a plot like this one. The aim here is to ask yourself the right question. If I want to make sure that my recall is always maximized, which is our case, we will try to ensure that we pick out these points around this. So we'll try to pick out these points towards the top right here. Let's take some of this off. So as we're saying, if we want to maximize our recall, it's but normal that we'll pick out threshold values which will take us around this region, because it's around this region that our recall is maximized. Let's do this so you could see that clearer. Okay, now the problem with picking a point around this is that when you pick a point around this, the false positive rates is increased. So you need to find that balance between this false positive rate and true positive rate. So it will be much logical to pick a point around this right here. So we could pick around this region instead of this previous region right here. Now you could see that in this region, or let's say we pick this point. If you pick this point, your false positive rate now is smaller, while your true positive rate is, or your recall is maximized, though it isn't the best possible recall we could have. But trying to focus on getting that recall of 1 will lead you into trouble, since getting a recall of 1 in this case will increase our false positive rate. And then if we're dealing with a problem where we're trying to maximize the precision, then in that case we want to ensure that this false positive rate is minimized. And so in this kind of problems, we will want to pick a point around this. So you see, we want to pick this kind of value, since at least our false positive rate is minimized. But then if you want to go and pick a point around this here, you would have a false positive rate of 0, but doing this will get you this into trouble, because here you're gonna have a true positive rate which is very small, and so you need to get that balance. Now if you're having a problem where it doesn't really matter, that is, you aren't trying to prioritize the precision or the recall, and working with the accuracy is just fine, then you could pick out this point right here. So this is when you are having, or you don't have to prioritize on any. Here is when you're trying to prioritize on the recall, and here is when you're trying to prioritize on the precision. But at least one great thing is with this tool, that is the Roc Plot, we are able to pick out this point and then automatically get that threshold we need to work with. And so when doing predictions, we will not, or we may not use 0.5, but we're going to use a certain threshold which will suit these objectives we've set initially. Now we'll now move to the area under the curve. For the area under the curve, we generally use this when we're comparing two models. Here we have this model. Let's call it model A. It's not actually this model A. It's a different model A. Let's call this model alpha. And then we have this other model, which we shall call model beta. So we have model alpha and model beta. It's clear that model beta is better because it gives us better options. Now you'll see that if I find myself here, I get a better true positive rate, false positive rate balance as compared to when I find myself at this position. And so if we are comparing these two models, we could make use of the area under the curve by calculating this area covered here. So let's bound this, and then for alpha we have this area under the curve, popularly known as AUC, A small u and then C, which will give us this. And then for beta, we're gonna have this area under the curve now, which covers this area plus this extra area right here. And so in general, if we have two models and then we want to compare them, then we could use this area under the curve, since it shows us how much freedom we have in playing around with these thresholds. We now get back to the code and see how we're going to implement this new matrix we've just talked about. So right here we have matrix, and then we have the false positives, we have the false negatives, we have the true positives, we have the true negatives, we have the precision, we have the recall, we have the AUC, and then since we're dealing with a binary classification problem, here we have binary accuracy. We run that, that's fine. And then right here, instead of having this matrix, we'll define this matrix list, which will contain these different metrics which we've just talked of. So we have the true positive, false positive, right up to the AUC. Let's run this, compile, and then feed our model. You'll see that as we train, we have the true positives, false positives, true negatives, false negatives, accuracy, precision, recall, and AUC scores, which have been given to us. As you could see, here are the results we obtained. We're gonna go ahead to evaluate our model. So let's get to the model evaluation. We run this, test data, and then we have our model evaluated. There we go, our model has been evaluated. As you could see, we have this loss 0.35, number of true positives 1323, number of false positives, number of true negatives, false negatives, accuracy, precision, recall, and AUC. So that's what we have for this model. For now, we have been showing you this binary accuracy, false positives, up to the AUC. What if we plot out the confusion matrix and also the Roc plot? So we'll import scikit-learn and seaborn. Right here we have scikit-learn, and from scikit-learn.metrics we're going to import confusion matrix, and then for seaborn we need to import seaborn and SNS. So that's it. So here we are importing scikit-learn and seaborn, which we'll both use in plotting out this confusion matrix. So let's run this, and then we'll visualize our confusion matrix. So we'll have to get the label that's the true values of the outputs, and then we'll also get the predicted values. So yeah, we want to get the labels and the predicted values. Now let's start with the labels. So here we're gonna have labels. We have this list. There we go. And then for x, y, or let's say for x, y in the test data set, we're gonna take this as numpy iterator. So for x, y in this, we have the x and the y, we have that, and then we append every output to these labels. So here we have labels.append y, and we run that. So that's fine. We could now print out labels. What do we get? There we go. You see we have these labels. Now let's convert it into a simpler form where we just have only these values in here and not this arrays which we have here. So in order to get that, we'll have labels will be equal labels, or rather will be equal an array, and in here we're gonna create this list. So in this list here, for every element of this labels list, so for here for I in labels, we're gonna do I the 0th index. So we're gonna take always this element right here. So that's set. We have that, and now we have labels. Let's print out the labels after doing this transformation. There we go. Here's our labels now. So we have that. Fine. Could take that off. We have this error actually because we tried we've converted these labels already, and then we're trying to reconvert them. So let's comment this right here. We comment that and run this, and we have our labels. Okay, now we have these labels. We could move ahead and get the predicted values. So to get these predicted values, we have our LeNet model, LeNet model. There we go. Dot predict. What we're gonna pass in this predict method is our input. So we have the input, and then right here we add this input list, and then we do same as we did with the labels. So we have input.append x, which is this input here. Now we run this, and then let's add a cell. So we add this code cell, and then we're gonna pre-process our input. So from this, we're just gonna print out the input to see what it gives us, or what kind of shape we're having right here. Let's put numpy array while that's loading shape. Then we run this other cell right here. Here's what we get as shape. So we have to take this off, this one off here. And to do that, you see we would have the input will select this first index. So we take that. And then for this next, we take only one. So we're going to chop this off. And then we have the rest. So that's it. Now we run this again. And we should have put a shape here. So we run that again, and there we go. So this is what we expect. Now we've gotten the labels, and then we are now ready to get the predictions. So here we have this input. We take this, and then we pass it in here. We pass our input, and we get our predictions. Let's print out the predicted here. Let's print out the predicted and see what we get. See what we get right here. We could print out a shape to better understand what this is. And as you could see, we have this. So how do we take this off, or how do we make it look like the labels? We could simply take this off. So we select the first, and then for this one we take it off. So we run that again, and there we go. So now we could do this, take off the shape, and then it should look like the labels we've had here, and that's it. So now we've gotten this. Our next step is to use the confusion metrics from scikit-learn metrics and produce our confusion metrics. Now let's comment this sections first. So here we've passed in the labels, we've passed in the predicted, and then we're specifying this threshold. So what we're saying here is all values greater than the threshold considered uninfected, and all values less than or equal to the threshold is going to be considered as containing the parasite, and then we're gonna have this in this confusion matrix here. So we run that, and then as you could see, we have our confusion matrix, which shows us the number of true positives, true negatives, false positives, and false negatives. Getting back to our model evaluation, we'll see exactly which of those values are the true positives, false positives, true negatives, or false negatives. So let's just copy this out here. We take this up, and we shall see that below. So here we have this confusion matrix, which we've just seen. Here is it right here. Confusion matrix right here. And then let's paste this out here. So we have the number of true positives. This one matches. And then number of true negatives, 1298. Yeah, this is closer. So what scikit-learn gives us is quite similar to what we had with TensorFlow, but they're not exactly the same. So this tells us that this is the number of true negatives. This is the number of, no, this is the number of true negatives right here. So here we have true negatives. Here we have true positives. Then here we have false positives. And then here we have false negatives. We'll then see how modifying this threshold will either reduce the false negatives or reduce the false positives. So let's have, say, 0.25 right here. We run that again, and there we go. Let's print this. So we see that we now have a number of false negatives reduced when we reduce this threshold. We now go back and then take this to 0.75. We run that again. You see that this is now reduced. So here we have a an increased number of false negatives and a reduced number of false positives when this threshold is increased to 0.75. So that's it. Let's now print out, or rather let's now plot out this more elegantly looking figure with the Cbun library. So here we go, we run that, and that's it. So here we have our same confusion matrix, but more elegantly plotted. Let's take back to 0.5 here and have that. Okay, so that's it. Now you notice that when we're trying to say reduce the number of false negatives or the number of false positives, what we're doing is we're just picking up some values here. Like we could pick up 0.2 and then we see its effect, and we could do the same for 0.25. You see how this takes us to 58 and this to 130. We could continue doing this until we get our best results, but then this isn't very efficient since we're just trying out different values. Now the way we could do this more efficiently is by working with the Roc plots, where we'll be able to choose a threshold in a more efficient manner using the plots. And so we'll be able to reduce the number of false negatives or the number of false positives without having to try out all these threshold values manually. The very first thing we'll start with will be to import Roc curve. So we have Roc curve, and this is part of scikit-learn metrics. So we'll run this again, and then just right here we'll make use of our method. It's going to output the number of, or it's going to output a number of false positives, true positives, and then thresholds, which we'll use in coming up with the Roc plot. So we have that. We have Roc curve, and then this takes in the labels, and then the predicted. So we have this predicted value. Now if you print this length out, the length of FB, length of TP, and length of thresholds, so we have exactly the same number. Thresholds here, we should have exactly the same number. Here we have 330. Okay, so now we have this. Now note that the reason why we need this is because when coming up with our Roc plot, like say we have this Roc plot, we want to have for each and every point the corresponding TP, FP, and then the threshold, which will lead to that TP, FP pair. So that said, we are going to make use of this data now and then plot out the Roc curve. So let's get straight into that. We have our plot, And then we do plotting, we pass in the false positives, true positives, just like x, y. So here we have x, and then here is y. Let's get back, that's fine. And then from here we have the labels. So we have x label, which is our false positive, and then the y label are true positive rate. So we've seen this already. Now we have this, we could include the grid. So we have this grid, and then we show. So that's it. We run that, and here is what we get. So this is our ROC plot right here, based on this FP and TP we got from here. Now, how do we include these thresholds? In order to include these thresholds, we are going to make use of matplotlib's test method. So we have plot.text, and then here we're going to have the TP, or rather the FP, TP, and then what the actual text will be put in here will be the thresholds. So we'll be passing in the thresholds. But now note that we actually have to do this for each and every point, which is impossible since there will be too many text put out here and it's going to be choked up. So what we could do is we could skip some values. So we'll say for I in range, we're going to start from 0 right up to the length. That's actually going to be 330 length of thresholds. And then we are going to be skipping some values. So skip, and then we'll define the skip. So let's start with a skip of 20. So initially we're going to skip 20 values. And then once we skip this value, let's pass this in here. Once we skip this value, we pick in a given I, picking that given I, same here. And then we do the same with the thresholds. So we get the corresponding false positive rate, corresponding true positive rate, and then the corresponding threshold. Now that's done, we could run this. So here's what we get. We see this plot. Now we could see the ROC plot with the different thresholds. I think we could let it like this. It's fine. Let's increase the size. And then we'll try to focus just on this portion, which actually matters the most, because we wouldn't want to get into those regions, because in those regions our false positive rate is going to be too high, and these regions below this would have a very small true positive rate. So generally we'll try to focus on this zone right here. Now, depending on the problem you are trying to solve, if your false positive rate is what matters the most, that is, if you cannot afford to have a high false positive rate, then you tend to pick values. Let's say let's break it out like this. So here is like the midpoint. We have some sort of mid here. Let's draw this line. Okay, so we have some sort of midpoint here. So this like 0.5, 0.46, 0.62, and all of that. So we're breaking it up like this. And then if you want to ensure that you try to minimize as much as possible your false positive rate without reducing your true positive rates too much, then you tend to take values around this. But if you want to make sure a true positive rate remains quite high, even at the detriment of the false positive rate, then you would tend to pick out values in this zone. So you have these two zones to pick your threshold from. This is the main zone, and then you have this zone right here, this other zone, and this other zone. So you have zone 1 and zone 2 from which you have to pick from. One other quick note is that if you have a problem like the one we're trying to solve, where parasite is 0 and then uninfected is 1, so this is how the data set was created, and this based on this we build our model, then this means that this will be considered as negative samples, while this will be considered as positive samples. Whereas in the real world, we'll tend to look at uninfected as negative and parasitic as positive. So you have to be very careful with these terms and know exactly how your data and models have been built. And that's why in our case, where we're trying to avoid situations where our model predicts a fake uninfected output, that is a patient who actually has a parasite, but the model predicts that's uninfected. This is actually a fake uninfected. This is a fake or false positive in our case. So we'll tend to minimize this number of false positives. Now, if your model was built such that parasitic is 1 and then uninfected is zeros, then it's clear that you will try to instead minimize the number of false negatives, since uninfected is considered as negative. That said, coming back to our problem, since our dataset was constructed in this way, we're trying to minimize the number of false positives at all costs. But while doing this, we have to ensure that the true positive rate remains at a reasonable position. And so we could pick out a threshold of like 0.6265 given right here. Getting back to this, let's take 0.6265. We run that. We have here a number of false positives to be 87, which is going to be smaller than when we're having a threshold of say 0.5. Run that again. You see 87 is going to be smaller than this 99, the value of 99 we're getting now. And so that's it for this section on metrics. Thank you for following up to this point, and see you next time.